Let's get a full screen, see what I'm doing. All right, so these are the graphs 58 through 70 on the test today. And the exponential decay problem that you're looking in front of you has a base, and you want to know the base. Then you look at the derivative on the right, which is 7, 10 to 17. The derivative on the left, 10 to 24, 14. And this is cutting things in half every 100 years. That's going to show up here. All right, so reading from left to right, we start with the most important y value, the fact that everything is above 10. All right, now we start measuring. How much above 10? 14. Next time it's not 14. 7. Now everything's the x values, and that's the same thing you do with the linear. 1800, x minus 1800, 1900, every 100 years. So we're cutting in half as we move to the right. If we move to the left, we're doubling. So instead of up 14, I'd go up 28. Up 28 gives us another data point of 1700. Should get us 28 plus 10, 38. All right, and I think it's useful now to throw a third value there so the concavity can be seen more clearly. Okay, I'm looking at a sinusoidal graph. What's the most important y value? The one in the middle. All right, so 40 to 100, 70 is in the middle. So that's where we start. How do we get to 100? We'll read left to right, add 30 units. Now I could do a sine or a cosine, so I'll do both. The sine function maximum height at pi over 2. So we'll do that as our first graph, pi over 2. So I'm going to do it as this, here, sine function. I can see that I've got one revolution, which is 2 pi, once around the circumference of the circle. So that's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. 1955 to 2002 took 47 years. If I'm not making any mistakes here. I'm going to make a 0 out of 1955 because I'm going to convert the year 1955. When I put the year 1955 in here, this all disappears. And I want to be located on the circumference of the circle at pi over 2. Because when I'm there, I get a unit of 1, which I multiply times 30, which makes it 30 times bigger. And I add 70, which brings me to the quantity 100. And 2.5 revolutions later, 1 revolution, 2 revolutions, boom. 2 revolutions later, I want 40, and 2 revolutions from 2.5 revolutions. So let's do 2.5 revolutions. There's 1, I'm back to a max. There's 2, I'm back to a max. A half a revolution puts me at a min, which is -1. I multiply it times 30, -30. I add 70, and I'm at 40. Cosine. I start walking around the circle. Well, cosine measures widths in the unit circle. They're a max when that's 0. So nothing changes. X minus 1955. I do not need to write plus 0, but that's where I am on the circumference of the circle for the cosine curve, and I get the same graph. I think the sine and cosine curve are basically the same function, but just off by 90 degrees. All right, 3x squared minus 6x plus 7, cup shape up. I'm on the downside for my y-intercept. Therefore, I know that's positive. 3 and a 6 goes twice. Cut in half is 1. Plug a 1 in, you get 3 minus 6 plus 7, which you like to see, the 2-to-1 opposite relationship. 10 minus 6 is 4. Moving on. Doesn't hurt to know the roots. I'm measuring 1 plus or minus the square root of, and this is where people are making mistakes. The square root of, the A term is 3, excuse me. A term is 3, so we know we got a division by 3. And we also want to get to 0. Oh my. I wonder how far I have to go. If you said you got to go down 4, you would be correct. And then I hope folks would realize that, yes, this cup shape does not cross the x-axis. So you are imagining things. What are you imagining? Boop, 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 the other direction. And then those x's would intersect where this thing intersects a height of 8. Right? 8. Does it hit a height of 8? Yes, that's not imagining things. Does it hit a height of 0? Heck no. All right. I was talking the other day on a video, and I think I drew a slope of -5. So I want to make sure I draw a slope of +5 this time. So we locate ourselves at 4, 6. That's what makes 0 equal 0. Okay, so let me write that over here because some folks are still having a little trouble with that. So I plug in 6 for y. I get 6 minus 6. 5 times plug in 4 for x. That's my x. That's my y. That's my truth. And if we go over 1 and up 5, because this is really a ratio of 1 to 5, I'm at a new location. And if I put 4, 6 there, and I go up 1 and up 5, then it's 5, 11. And I hope I didn't make a careless error because I'm not thinking about that too much while I'm talking. Okay, a little tight here, Renee, a little tight. You negotiated that well. All right, so square root function, square root of x, starts at 0, 0, 1, 1, 4, 2, etc. Eventually, 25, 5. And that's the one I like. I like to use that number, square root of 25. So what do we have? Well, I don't have 0, but I can make a 0 with -3. I don't have 0 out, but I can get negative out by plugging -3 into the equation. And that gets me started, and it's a positive. This was a positive times 1. So things are going to go up twice as fast as that, starting from a new location. So there we go. We're going up twice as fast as that, starting from a new location. I like 25, so I'll put 22 in here. And it looks like I've got 10 minus 8, 2. So what's the rise? -8 to 2, 10. What's the square root change from -3 to 22? 25. And it's coincidental, I guess, that that's a 2. Rise over square root of run as measured from the endpoint. So what's the domain of this problem? X's are greater than or equal to -3. I want to start looking at domains that are not all reals. Range, y values are greater than or equal to -8. That describes the table values that you get out of this function. Well, e to the minus x plus 5. So I know I'm going to want the framework of a 3 to 1 ratio here, except that my first jump is going to be 12. And my second jump is going to be 1/3 of that, 4, if I pick the right numbers. Minus x. Well, I hope you're seeing plus 0 over 1. All right, so no, actually, e to the I'm going to use 1.1, so take that back. I just made a mess on the floor here with this ink. A little bit. Take care of that later. All right, back up again. So I've got this framework. I know I want a 3 to 1 ratio. What's going to give me a 3 to 1 ratio? An x value of 0 and negative and 1.1, excuse me. 1.1. That gets me the 3 to 1 ratio. So, how am I going to get 1.1 out of that? Well, I hope you say I'm going to put in -1.1. 0 is not hard. All right, so I would have started with 0. E to the 0 is 1. First jump 12 plus 5, 17. So let's see what we have. We have y equals 5. We want to put a 0. Put it in the middle. If you're not quite sure where you want to put it in the middle. So 12 plus 5, 17. Now, what makes 1.1? -1.1, which is on this side. Okay, so -1.1, we'll put it there. And then we'll get better at the 3 to 1 ratio drawings as we work a little bit more with exponential decay. So -1.1, if we put -1.1 in here, there's a double negative, so that's +1.1, which makes 3 times 12 is 36, on top of 5, 41. And you're trying to visualize these. You don't really, draw these as part of your graph. but you're trying to visualize that. So 36 and 12. You can see the 3-to-1 ratio, and that's what we're going to do with e to the x. We're always going to standardize it and make a 3-to-1 ratio so that we graph these quickly and easily. Now, there's going to be a 2-to-1 ratio in this direction. 2-to-1, which means this is going to be a half, and I want to start having folks graph a third point here after midterm to help get a little sense of concavity. Probably should have been doing that right along. So what am I seeing? I'm seeing x minus 4 over 1. What numbers am I going to pick to start? 4 and 5. And then I want to jump a 2. I think I'm going right to 6. All right, so x equals 4 is the asymptote. So we want 3 situations to look at. We want log base 2 of 0, which is undefined. We'll just use that, the null set. We want log base 2 of 2, which is 1. And I'm sorry, we want log base 2 of 1, which is 0, because we're going to be multiplying, right? There's a multiplication here. And that's a nice thing, because that makes that multiplication disappear and you get this number. And then we want log base 2 of 2. That's nice too, because that makes this 1. And that gets us 10 times 1 plus 5. This one gets us 10 times 0 plus 5. And that happens every single time. So if you put the effort in, then you can come over here, you can spot the 4. You can see what makes it a 1, a 5. That's going to get us a 5. And you can see what makes a 1, a 6. That's going to get us 15 without even looking at the problems. There's our jump of 1 unit. There's our jump of 2. So what makes a half? A half is going to occur with a jump of 10, right? That's a jump of 10 in that direction. So we should be able to get -5. Let's move the asymptotic equation over here. X equals 4. And we've got ourselves -5 occurs when x is 4 without even looking. And that's going to be, let's see, that's there. So a good place to draw that would have been right about there. That's a half. And then if you said, yes, a 4th here, an 8th, yes, that's going to happen. And that means that distance from 4 is shrinking. And if it keeps shrinking, then we have asymptotic behavior where the y values are changing rapidly, but the x's aren't changing much at all. They're kind of hovering around x equals 4 over here. Okay, so much for that one. Well, let's come back just to prove to you that 4 gets us what we said it would. Otherwise, I got to do the video again. So 1/2 plus 4 is 4.5. 4.5 minus 4, I got an eraser here, is a half. We started with this on day 1. Log base 2 of 1/2 is -1. And now maybe you're getting a little better sense, a deeper sense of how the numbers are changing in this logarithm. That's the hope. Okay, so what's the hope here? The hope here is that you're seeing 2 numbers immediately, 5 and 7. 5 and 7, just like the linear function. Right? Those are my x values, and I'm hoping you can see that 5 is going to get us a first jump of 4, so that's going to get us 10, and 7 is going to get us 12 plus 6 is 18. So let's see if that happens. Exponential growth. This is bigger than, so we got a 3-to-1 ratio, 3-to-1 ratio. First jump, second jump, 3 times as big, so that's in the mind's eye. So here we go, we look for that 3, I'll put that there. What's 3 times that? I'll say that's right about there. What x do I want? I want a 5. What's the y value? Y value is 6. All right, what am I going to get if I put a 5 in? I'm going to get 10 without even putting 5 in and doing the math. What am I going to get when I put a 7 in? 12 plus 6, 18. Now you need to recognize that every 2 units, the differential is increasing. Well, let's look at it this way. All right, so if that's 3 times 4, and that's 12, then over here is 4/3, a jump of 4/3, and that's going to happen when x is 5 to 7 is 2 units. So over here, we should get 3 and 4/3 plus 6 is 7 1/3. I'll write it that way. Okay, that should happen. Let's see that one happen. 3 minus 5, -2, divided by 2, -1. Well, what's 3 to the -1? 1/3 of 4 plus 6. I'm hoping that you're seeing these things. And if you are, you're working a whole lot faster now than you were 2 months ago. 2 months ago, I couldn't do it. And if you can do it now in under 10 seconds, that tells you you're doing something called learning. All right, sine function. So sine function measures heights on the unit circle. Here's your circumference. How far have I moved? I haven't. 0. Here's another spot on a circle. How far have I moved from 0? Whatever that radius is, 6.28 times that radius is the distance I moved. But we want a unit circle, so 6.28 units. I hope you say, wow, that sounds like 2 pi. And you'd be right. So where does this start? 0. Where does it end? When 2x equals 2 pi. If you want to know the period of a sine function, you always take the multiplier. You take that multiplier, which in this case is 2, and you divide it into 1 revolution. And so therefore this has 1 revolution. The period of this is pi units. All right, so we're going to start at 0, 10. We're going to go up 4 units to 14, and then we're going to come back to it, and we're going to stop when x is pi. 2 times pi is 1 revolution. We're back to 10. So this is how I would have done this without talking to you. I would have gotten a framework. I would have put 10 here, 14 there, and 6 here. I now know the range is y is less than or equal to 14, greater than or equal to 6. That's a question on your test that some folks haven't gotten right yet. So here we go. There's the framework. I know I'm starting at 0, 14, 10, excuse me, and coming back here pi units later, because I'm doubling, I'm going twice as fast around the circle as normal. So normally it might take me this length of time, but if I'm going twice as fast, I'm cutting my time in half. Yeah, I hope that's a decent analogy. So back to 10 here, which means that this is pi over 2 and that this is pi over 4. It doesn't hurt to see pi over 4 getting 14. So let's just look at how pi over 4 ends up at a height of 14. So pi over 4 times 2. Pi over 2. Where is pi over 2? Oh, that's the top of the circle. What's the height at the top of the circle? 1 times 4. 4 plus 10, 14. So a lot of symmetry here. All right, the ln function normally has an asymptote at 0, but we've shifted right. I can use the word shifted right. 3 units in terms of where we're looking. So the language does work. I've got definitely an x minus 3 over 1 with a base of 2.71, but I like the following numbers, ln of 1 and ln of 3. Those are the numbers I work with. ln of 0 gets us undefined, which in this case is 3. What makes a 1? A 4. What makes a 3? A 7. That gives me a ratio of 1 to 3. What goes with a 7? ln of 3 is 1.1, 5.5 plus 7, 12.5. What goes with a 4? ln of 1 is 0. So immediately I see a 7. And there we have it. I can start learning to move that here because I am going to ask folks to, get a sense of another value here. Well, 3 to 1, so that's going to be 1/3 the distance, right? That's a jump of 1, that's a jump of 3 differential, so that's going to be a 1/3. So 4 and 1/3, 3 and 1/3, excuse me. 3 and 1/3 makes this the ln of 1/3. which I've asked you to memorize, which is negative. Negative 1.1, excuse me. It took me a moment to get the brain cleared. So I'm going down 5.5. This went up 5.5. Now I'm going down 5.5. So 4 1/3, 3 1/3, excuse me, 3 1/3 should get me, take away 5/2, take away another half, 1 1/2. All right, and there's a pattern here that I'm hoping you're seeing, because I'm pointing it out. Which means I hope you're thinking about what I'm pointing out. Hope so. Kind of like to see everybody do well. So x minus 5 cubed, we know what x cubed looks like. It looks like that. So this is going to have a table value, not at 0, 0, but at 5, 0. So we've got 5 getting us 0. Then let's put a 6 in because this is over 1. 1 cubed is 1. Let's put a 7 in because this is over 1. Let's put an 8 in. It's over 1. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. And in the other direction, 4, 3, 2, we're going to get minus 1. We're going to get minus 8. We're going to get minus 27. And I call these user-friendly numbers. User-friendly, yes. I don't need a calculator to do that. I know when I put 8 in, I get 3 cubed, and I know that's 27. So all we do is change this to 5, 0 and show one other value that lets me know. Well, maybe we can try, how about other than moving 1 unit, let's move 2 units. Let's move 2 units, and let's call that 7, 8. That's all I'm looking for. You've communicated to me. You don't have to put in all these other numbers. If you know the shape and you know a couple, I have confidence that you know what you're looking at. What's the sine of 3.2 negative 0.06? You can try to figure out how I know that. That's an approximation for that. That's been drawn a number of times in previous lesson sets. It's a rehashed problem that's been asked on worksheets and on tests. You know, the first time I asked this question, I said, what's the sine of 3? And it's approximately 0.14. I've only had 1 or 2 students ask me why. Hoping I get more, catch a few more people along the way. And that's the graphs. All right. So Yasser, I'm hoping that's taken less than 45 years to learn how to do. I think it is. And I think that that's true of every problem we're doing. So do these lesson sets. You get right where I am. I've got kids doing those quicker than me now. Okay. Young, let's see, stay safe and warm. Off we go.